Hello guys, welcome back to my channel. Thank you, boy. During university, I have spent a lot of hours to study about the fundamental of chemical engineering, such as process control, separation, design, transport phenomena, and others. But after entering industry, I realized something surprising. The subject wasn't wrong, but the focus was different. Nobody asked me to derive the Navier-Stokes equation. Nobody asked me to draw the Mercantile diagram. Instead, I was asked to optimize a plan. I was asked to troubleshoot problems. And people also asked me why the production is dropping. So today, let's talk about chemical engineering subjects which students may be focusing on the wrong things. Before I start, as a disclaimer, this is not the criticism to chemical engineering education. So the fundamental is still extremely important. And in fact, everything we do in the industry is built upon those fundamentals. However, many students become so obsessed with the derivation of equations, calculations, and also textbook problems, while missing the important key of the practical engineering mindset that industry actually values. Let's take process control as the first example. In university, we learn how to derive a dynamic model equation. We learn about how to tune PID using Ziegler-Nichols, IMC, Cohen-Kuhn, and others. We calculate the gain values and the time constants and learn how to tune the controller mathematically. But in many industrial settings, engineers are not starting with a blank sheet of paper. Most control systems already exist, and even vendors already providing the recommendations on tuning values. Most of the time, tuning is performed through gradual adjustment and also trial and error. So in my opinion, the key thing here is that we need to focus on understanding the effect of tuning parameter change to the response of the process. So what is the effect if I increase the K? What is the effect if I decrease the tau I? So that's the focus that we should have. From what I have observed, usually tuning is the last thing that engineers will do. Before touching the tuning parameters, engineer will typically ask, is the control valve healthy? Is the instrumentation calibrated? Is the process condition changing at the upstream or in the downstream? So the real skill is not only the PID tuning, but also understanding the process and the problem. Let's take distillation as another example. During university, we learn about distillation column designs by calculating the number of stages, reflux ratio, separations requirement. But when I look at the actual industrial problems, the question is rarely, please design a brand new distillation column or please draw a makeup tail plot for me. But instead, the questions are why the product purity is dropping, why the steam consumption in the reboiler is increasing, why the top pressure is not stable, and etc. So we could see that industry spends more time to troubleshoot, to optimize the existing columns rather than designing a new ones. The design knowledge, however, is still important because it will help us to understand about the columns. But more than that, we need to understand about the operation of column. What is the effect if we change the reboiler temperature? What will happen if we increase or decrease the reflux ratio? What should we do if the temperature in the top is decreasing, and how it will affect the purity of the product? That kind of questions we need to understand because it's very critical in the plant operation. Almost all chemical engineering students spend their last year in university to design an entire chemical plant as their capstone project. And honestly, this is a very excellent exercise. It forced the student to use and to integrate the knowledge they have learned for the last 4 years, and it will help students to know what is the implementation of each subject to the plant design. However, after graduation, many engineers discovers that their daily work is totally different from designing plants. This kind of practice usually only done by someone working in EPC or in process licensors. But for the others, instead of designing a brand new plant or brand new equipment, engineers often challenge to increase the capacity, to reduce the consumption of energy, to replace equipment, to resolve the bottlenecks of the process. In equipment design or process design, usually you already have a very clear methods on how to do it. And even probably you already have an Excel templates to design an equipment. However, in process improvement and also troubleshooting, usually you don't have a very clear methods Some says that it is a mix between science and also art because every engineers can have a different perspective, different methods, and different approach. Because of that, in my opinion, improving an existing system is very hard. It requires technical ability, it requires creativity, and a deep understanding of the process. Sometimes we are facing also with constraints that we cannot ignore, and these constraints will make the improvement percentage become lower and our room for improvement is less. But you know what? If we are able to just make it 1% of the improvement, for example, in steam utility consumption, it is a very big business value for the plant. Transport phenomena might be one of the best example. Many students think that the goal of this lesson is to learn how to derive equations. And some also say that this subject is actually mathematics, but in other way. We spend countless hours to derive the momentum, heat transfer, and the mass transfer equations. But let me ask you a question. How many engineers have been asked to derive a Navier-Stokes equation during plant meeting? Probably it's very rare and very few. But the concepts behind those equations are very useful for everyday work. Let me give you some examples. Understanding the velocity profile will help us to understand why the pressure drop increase, why the mixing become less ineffective, why a certain parts of the system have poor flow, why there is a stagnant flow in a certain joint of the pipe, and understanding the temperature profile across the walls and the heat transfer surface also will very help because in industry engineer will use this understanding to locate where is the heat transfer resistance when a heat exchanger is working poorly. So the key focus and the real value of transport phenomena is not on the memorizing the equations or even deriving the equations, but how we can develop a physical intuition about how fluids, heat, and mass move through a process. So the big question is chemical engineer learning the wrong things? My answer is no. The subject themselves are important. Process control, distillation, mass and heat balance, all of them are very useful. The issue is that students sometimes too focus to the calculations and to deriving the equations while forgetting why this concept exists in the first place. The equation is only a tool for us to understand about the phenomena, about the problems, but understanding the process, identification of the root cause, communicating the solution, and also making practical decisions are what create a value. So guys, I'm very curious about your experience. If you're a student, what subject do you think you feel disconnected with the industry reality? And if you're already working as an engineer, which university subject that turns out to be very different from what you have learned or from what you expected? Let me know in the comments. So that's it for this video. I hope this will be useful for you and see you in the next episode. Bye bye.